All right. So I was talking about basically building on the concept of MDP, and we talked briefly about model-based, model-free reinforcement learning. And then we talked a little bit about the temporal difference learning, right? Because we said that in reinforcement learning, in real world environments, it is not possible basically to take all the samples at once and then take the average because it's just simply not possible. You cannot go in the past and do the average. And if you just do the average based on, let's say you take just the first step and then you want to do the average is going to just doesn't mean much because it's not the true average. It's going to be a very bad average that you're going to have. And then in order to solve that problem, we discussed temporal difference learning. We said that instead of taking the average of the future, possible states, what we do is we let the agent make a move in the future and we update the value of the state that we just left. Like just update the past, just update the values of the state where you have just left that position, right? So we talked about, temporal difference learning by one step look ahead. Okay. So we said that, state, action, reward, and next state that you can get into, and then the action from the next state from the future state. That's what's called SARSA. So temporal difference basically is nothing but a one-step look ahead SARSA. What we can do is we can improve temporal difference learning, and we can look at multiple steps in the future, like n steps in the future, like 5 steps in the future, 10 steps in the future, right? So suppose that if I design an agent and if it stands in here and its job is to leave the door, leave this lecture hall, then the entire future is going to be, up to that point when the robot basically leaves the room. So you can basically take a look or look ahead several steps in the future or just one step. It's just, adds either more complexity because you're looking at, further more steps in the future, or it just makes the game a little bit more complicated to learn. It takes more time to just learn the game. But we'll talk about it. We'll talk about the n step SARSA to solve a real problem today. So we'll basically write the code for n-step SARSA algorithm. And I will show you the algorithm. So now today is basically the time to start using the Bellman equation to see how the real world problems are solved. We're also going to use an environment that you can use is called GIM, and it is an open source environment released by OpenAI. We're going to use the GIM environment basically to create a simulated world, right? Because we don't have the hardware here. So we're just going to use a simulated environment in which we're going to be able to see the graphics using Python. So the good thing about the environments is that suppose that you want to solve a problem, okay? So I'm going to talk about teaching an ant or a cheetah or a walking humanoid how to train them. It's pretty costly. It's not, it's very expensive to design a hardware, ant or hardware robot, cheetah or humanoid, to basically then train it, because how many times are you going to train it? The number of times you're going to train it, there are higher chances that you're going to destroy it, you're going to damage it, right? So what people do is they create a simulated environment in the software which represents the actual hardware. But you do things or you do the simulations in a simulated environment, and once your algorithm is trained, you load that model into the actual hardware. And then it works just the same as you were working using the simulations. So we're gonna use an environment called GIM that provides the simulation for a problem that what we're going to solve today. Okay, so once again, what we're going to do is we're going to talk about reinforcement learning. We looked at several different words, terminologies, right? We said that we have the state space, we have the action space, the agent perceives the environment, gets the reward from the result within the environment, right? And then we looked at the reward function, and we said that the biggest difference between MDP and reinforcement learning is that reinforcement learning is actually online learning. You let your agent or your program interact with the world, interact with the environment, and basically learn as it goes by taking multiple steps or multiple episodes, right? So we talked about quite a few terminologies like set of states, set of actions, a model, a reward function. We were still looking for the policy, right? Within the environment, we let the robot or agent interact with the environment, and then we continuously update our policy, our strategy, right? Because in reinforcement learning or MDPs, we really don't have the plan. We have the strategy, we have the policy that we continuously update based on how we interact with the environment. Why does this not remove? Oh, okay. So the main difference between the MDP and reinforcement learning was that in MDP, we really knew what the T and R is, right? What the T and R are, the transition matrix, and then the reward function. Something like this. Remember, we covered a very classic, our class dynamic example, where we said that there are several different classes, right? Like class 1, class 2, class 3. If you do really well, you will go to class 2. If you feel tired, you'll start taking, you just take your device out and then you'll start using either Twitter, your social media, or you can go to a bar in a certain situation. That class dynamics example that we did, it was something like this, right? So we had multiple states, S1 up S to N. So S1, A1, we can take several possible actions like this, SNAN. And from this one particular state, you can take a particular action, and then it will land you in a separate state. And what we do is we will simply have this transition matrix. So we actually have the T known in MDP. And then we also had the reward function. So the difficult thing in reinforcement learning was we really don't have this. We either normalize it, remember, we either directly average as we go along in the environment, right? Average, and we get the T and R, and then we simply just follow that, either model-based, or we simply don't even have that. Without even having that information, we apply temporal difference learning, and as we move along, we continuously update our values, right? So with temporal difference learning, we had a continuous update. It's an online learning policy. It's an online learning algorithm that we continuously update the value, okay, state value function, state value, right, using temporal difference learning. But the problem with temporal difference learning was, if you remember, that it doesn't provide us any information about the action to take at each step. So we also have to be very careful about choosing a certain action that gives us the maximum possible reward. So we also touched based upon the Q learning part, like how we can do the Q learning. And then we would, apply different equations. So I'm going to go over just a couple more slides, I promise, and then we will start programming one example. So this is basically an overall view of what we have done, what we have covered so far. Something like this. Remember, we started with an example like this, where this one was the wall. We had a diamond here in this state, and then we had fire in this state, and it was -1. This was +1. Our agent was somewhere here probably, and then we had the policy, right? Something like this, arrows. Something like this. Something like this, right? So basically, what we did was we had the MDP, we know the environment, we know the policy, we are given an initial policy, right? What we do is then we compute the V star and Q star, and then we update the policy, right? Evaluate a fixed policy. We use value or policy iteration. That was MDP. That was basically an offline solution. Remember, we said that we're sitting and we're thinking, what if the robot moved left? What if the agent moved right? What happens? So you're just, those things were happening only in your brain. So that's an offline learning. And then we said that what happens if we don't know the MDP? If we basically, when I say if we don't know the MDP, it means if we don't know the T and R, what happens then? Well, with one technique, we can basically construct a model, right? Construct a model assuming that we know about how the world works. So we construct a simple model, and then we simply just solve that MDP. Solve that MDP using just value iteration or policy iteration on that approximate model that you have created. But then we also had the unknown MDP where we don't even have the model itself. Then we apply Q-learning because we really don't know what actions. We really don't know what actions to take. We really don't know any T and R. So we apply Q-learning, meaning we update our Q values as we move along in the environment. TD doesn't provide that. Temporal difference learning only updates the value, state value, but not the Q value. So there is a little bit of a difference between the Q-learning and temporal difference learning that we will look at today, okay, in the form of the code. We said that we're going to use the equation, like update the Q value of the next state by looking at the value of, all possible future states as prime, right, and get the maximum. And then just simply add the reward and then simply have the probability, right? Have the weighted average of that. But what's wrong with this equation so far that we have taken a look at, like a very detailed look at? What's wrong with this equation so far? Assuming that we're in the real world. Exactly. We really don't know what TNR. We really cannot use it, this equation. So what we have to do is we basically take samples, right? We take samples and then we just simply average those. Okay, so we will apply a sample-based approach. But one thing that we will remember, that Q-learning basically is an off policy. What we do is you are first given a target, or we will call it fixed policy. You're given a fixed policy. Okay, you're given some errors, but then for a maze world. But then what you do is you take a lot of samples and then you see if you can update that policy, shape up that policy, and find another way, another version of the policy that gives you the better reward. So what you do is you have a fixed policy, something like this, and then you have a behavior policy. Then you have a behavior policy that you learn and update as you go along to reflect your target policy. Okay, to reflect that. So we have basically a target policy that is given, fixed policy, and then you update your actions as you move along by taking several samples. Okay, so we instead of applying that T and R, we really apply, the Q exponential average from multiple samples that we have. Okay, so I'm gonna move on to this slide because basically the exploration versus the exploitation, the trade-off between. Does anyone remember what the exploration versus the exploitation was? The trade-off between these two. Basically, like how much do you explore versus how much do you exploit as you learn, in the real environment. Something like this. Now you suppose that your robot is standing right here. This is all fire. Something like this. And this is the main reward. and this is also file. And suppose that as you go along, you basically, find that it is a better way to go this way from here, and then better to go this way. And eventually you learn that this is basically the best path to choose to maximize the reward, right? But this comes after many, many simulations, many, many routes, like something, in one complete episode, you might, go this way. You probably will go this way, and then you will go this way and then find out what happens. That's one episode because your game ends at that time. Next time, you probably go this way and then fall into the second pit and see what happens. So you apply this algorithm multiple times and then find out that, this was the best possible route that gives us the maximum sum of returns, right? Now, exploration and exploitation, now see what happens. Suppose that after a very long time, after a very, very long time of simulations and observation, you say that you're in a certain state right here. You're in a certain state. Exploration means every time you make a step, you decide whether you choose the action based on complete randomness. Like what happens if you just either flip a coin or roll a dice and say, if it is a 4, I'm going to take a right. If it is a 1, I'm going to take a right, etc., right? You're completely random. Now, suppose that you're in this situation, it learns that, going this way basically is a better, option or better action because it gives you a better reward. Now, suppose that after 100,000 times, you get into the same state and you say, yeah, you know what? Out of 100,000 times, I saw that 99,099 something, 99% of the time, it took an action east and it was a better action. It was a better action, but I'm going to still be random. I'm still going to explore. So you basically, what you do is you explore a lot, but then you keep crashing. You're going to get the same result, all right? But you're going to keep crashing your resources, without any good use. So what you do is over time, when you learn over time, you get more and more, smarter playing the game. You exploit the situation, say, okay, what happened when I was in this situation before in my previous episodes, and how to play optimally in this step. So you just actually look at in the past and say, oh, wow, this was the best situation at this time. So you use the max function and say, just give me because I know enough about about this state, and I took a certain action, let's say I took an east action to the east, and that was the best reward. So give me that best reward this time. So what we did was that basically that algorithm is called epsilon greedy. Epsilon is a metric or a parameter that we set to decide how much we want to explore versus how much we want to exploit at a certain point in the game. Okay, something like this. So you see, you say at every step, you flip a coin. Basically, what you do is you generate a random number, right? In Python, if you talk about the programming language. So if that random number is less than the epsilon value, then choose a random action. Otherwise, choose best action, meaning use the max of QSA, right? Use the max function. That's the best action that you can choose. So you look at this, and then as the time moves along, you update your epsilon. So you start with 1, so your random number is always going to be between 0 and 1. So you're exploring more, much more in the beginning. But as the time goes along, just continuously reduce this value, epsilon, so that when you draw a random number, there are more often times than the random number is going to be greater than the epsilon. So then you become more and more, smarter, and you just pick the smart actions or the best action, choose the best action. Okay, so let's talk about very briefly about what we are going to code and program today. So just look at this equation. We're going to talk about a lot about this equation. So SARSA algorithm, what it does is you are in a state, you took an action, and you are getting into an S prime, and you're getting a reward. So SARS, and then what is the best action to take to choose from that current state? What we do is, you see, we're only looking at one step ahead here, right? Just one step ahead. And we are seeing like, what would be the action to choose in here? There are not multiple actions here. We're just only having one action, then that means we cannot use the max function here, right? So temporal difference learning, or TD learning, is one step look ahead online learning policy. All what it does is you just look at one step ahead and do the exponential average, but don't use the max here. We cannot use the max here because all what we have is just only one action possible. So that's one step. That's one step ahead. It's something like this. What happens if you choose an action, you get to a state, then you have another possible action, you get to another state, a future state, you can take another possible action, you can get to another future state, etc., like this. So that's like three steps. Three steps, Sarsa, right? If you talk about n as equal to one step, like one step ahead, look ahead, that's exactly TD learning. So SARSA basically is a TD learning, but it's one step look ahead. If you increase the number n to infinity, that becomes an incredibly difficult, problem to solve, because now you're looking at all the way in the future, right? That's when you really make use of Monte Carlo simulations instead, okay? So based on the problem that you're going to solve, it depends on how many steps you want to look ahead in the video. If your problem is really small, you can basically have a lookup table or look in the future all the way when the game ends, because you only have just like only a few steps ahead, right, in the game. So you can take a look at all possible steps all the way up to when the game ends, and you can program that. So we're going to talk about a game where n will be equal to 16. Okay, there's this book that I'm going to share, and I'm going to upload on Canvas, that actually provides us the algorithms for these major algorithms that we're gonna talk about. It provides the pseudocode, okay, for most of these algorithms. Here's the pseudocode for the SARSA algorithm. As I said, it was probably less than 50 lines of code or something. Using that 50 lines of code, you can solve multiple problems, real world problems, and we're going to solve one of those. All right. So what we do is we initialize some. By the way, now I say that, like, I'm looking at 10 steps ahead. Let's say 10 steps ahead in the future, and I'm updating my current state that I'm just leaving based on the 16 steps ahead, right? So that means I actually have to keep the outcomes or the rewards or the values of those future steps in the memory somewhere in order to update the past, right? Because we're assuming that we're going 10 steps in the future. So we have to store all those values in order to do the average, right? And also in order to do the sum of rewards, correct? Like what we've been talking about, the G, the value G, and then the immediate rewards, right? So we have to save and store them somewhere in our algorithm in order for us to be able to learn, right? So we're going to use some data structures, okay? It's going to be mostly one-dimensional or two-dimensional arrays, all right, within our code. And you will see how easy it is in Python to just simply program or initialize a data structure and just simply use that in your code. You may have already seen that in your first two homework activities. So we're going to use some of the data structures to store some values, and n step SARSA, when we look at n steps ahead in the future, that means that we are basically replaying the experience that we built. Who's calling? Nothing. It's vibrating, but there's no call or nothing. All right. So that means it's the experience replay. It's called the experience replay. So every time when you just like, look for code like this or n-step SARSA, a lot of the people are going to talk about or are going to use this word, say experience replay. We use experience replay. All what that means is for n steps, you collect these values, you store them, and you get basically the sum of the rewards, et cetera, and then you utilize that in order to update your current state. That's the experience replay. All what you do is you basically have that experience from taking multiple steps in the future and update your current state. That's it. Okay. So we're going to use the experience replay. It's called experience replay. Okay. So what we do is what we have here, like, we're going to initialize some of the parameters that I'm going to talk about line by line. Okay, line by line. What do we mean by QA? Because what we do is, you see SARSA. SARSA needs to store states, right? State, action, and reward. Three possible things, right? States, action, and reward. Look at how many different abbreviations are, not abbreviations, letters are used in SARSA. SARSA, right? So we're going to have states stored in our experience replay. We're going to have actions stored in our experience replay. And we also are going to have rewards stored in our experience replay. So we're going to use some of these data structures for these algorithms in order to solve this problem. Okay, solve the problem using the algorithm that I'm just showing. Okay, so there are some data structures that we're going to use. Okay, the problem that we're going to solve is how many of you have either played or heard or have seen the card pool? Card pool? Card pool? He must know because we did last time, right? Okay, so card pool is like a string, right? On the string there is a, let's say, wooden card installed that can just move left or right, and then there's a pole standing on it. And all what you have to do is you'll have to move the card left or right in order to keep the vertical position of the pole on top of it, right? It reminds me of the game that we used to play when we were kids. We would play this game, something like, we can hold a stick on our hand and then walk and then just keep the balance, and whoever walks for longest was going to win. So it's kind of a similar game like that, where what you do is you have card pole, right? So you have a card pole. Okay, card pole. What you do is, so your card basically can move either right or left, right? And then there is a specific end to that string. Okay, so we can solve this problem. Okay, what is the reward or the purpose of this game is to, keeping the balance, right? Keeping the pole in the vertical position for the longest possible time. The longer the card can keep this balance, the higher the reward, right? The higher the reward. When does the game end? Well, there are certain rules to to finish or to end this game. One possible situation is that when the card basically goes way to the right, like too much to the right or too much to the left, that it hits these walls. That's it. Then the game ends. Because it was trying to keep the balance, but then it has reached the end. It has hit the end, and the pole is going to fall down. right? And then the other possible termination of the game is that when there is a certain angle of the pole, it goes beyond the, because the angle at which it's standing, first, it has to have make a 90 degrees angle with the card, right? If the difference, or if the angle goes above certain threshold, let's say 5 degrees, if it goes either to the left or right 5 degrees or more, the game ends, because that's when you just can't keep the balance anymore. So there are two possibilities, right? Two possible, terminal states. So we have the terminal states, we have the start of the game, right? We now have so let me tell you like how we are going to extract basically the state space and the action space for this game. All right. So what do you think are going to be the states of this game? States. Left and right, these are the actions, because card can move either left or right. So that's the action space. You basically have told us the action space. That's great. Now, how about the state space? Okay, so the pole's position, right? Not position, the pole's angle, right? What the angle is, and how fast it is moving in certain direction. How fast it's going either in a negative, direction or positive direction, right? So these are the two states for the pole. How about the card? What do we need to know about the card? Exactly. What's the velocity? How fast is it moving, in a certain direction? And what is its current position? Right? Current position. Because it's just one dimensional, it can only move left or right. It cannot move up or down. We just need a one dimensional position, right? Just the X value. Yes, Ronald. Sorry? State space. It's a state space, yes. It can have multiple, so the game can have multiple states. So what we do is, yes. So what we do is we have action space, which is A, which belongs to either left or right? These can be just the only two possible actions that we can take. Move the card left and right. We don't have a control over the pole. We'll have to move the card left or right in order to keep the balance. So two possible actions. Everybody's happy with that? In terms of the data structure, we can put this as A. If it is 1, then we mean it is going left. If it is 2, it means we're going right. Just an array of 2 values, that's it. Or you can call it 0, 1. 0 means left, 1 means right. Or 1, 2. 1 means left, 2 means right. So far, so good? Yes? Okay. Then we have state space. State, that belongs to, we have pole theta, right? Pole's angle, and pole, let's say, theta velocity, how fast the theta is changing. Then we have card X position, right? And then we have card velocity, right? Card velocity. Make sense? These are the 4 states that we have. But now pay close attention. These are all continuous variables, right? These are all continuous variables because a theta can have a number between 0 and 1, there are infinite number of numbers, right? Because you can put point, 0 point, and then put a trillion zeros, and then put a 1 at the end. And then you can basically have a continuous or infinite possible numbers, right? So these are continuous. What we're going to try to solve today is using the Q-learning or temporal difference learning that is going to be for discrete state space and discrete action space. Nathan. Remain stationary? So don't you think that remaining stationary is not taking any action? Like, don't take left, don't take right, and just don't simply change the position. That means we're stationary. That means we are already embedding that situation. Exactly. Implicitly, we're embedding that situation, right? So once we learn, we will like the cart will stay, will remain stationary, and it will only move when there is a certain movement in the pole. So it's already implicitly embedded there. So we really don't have to use that. We can do that. We can say remain stationary. That's fine. But we can have another additional state. No, not additional action that we can have. That's fine. But it's already implicitly there. Okay. So these are continuous. We will talk about the discretized version of these states, right? Because we're not going to get into the situations where we're going to start solving continuous state space or continuous action space, because that's much more more complex, more complicated. We will start with some basic examples, right? So if we look at this figure, what we do is, what do we need to remember, need to have in our experience replay? Well, we need to know what our current state is, right? We also need to know what action we're going to take. Then we also need to know how much reward we are going to get. And then we also need to know what is the future state that we're getting in, and what is the next possible action that we're going to take in order to go into further next steps, right? So these few things that we will have to remember, right? At each state, we're going to choose an action, right? We're going to choose an action. So we're going to have a helper function called choose an action, right? Choose an action. In our game, it's going to be either take left, not take left, move left, or move right, right? That's a possible action. But remember, we're going to do epsilon greedy. Every time we're going to flip a coin, and if the random number is less than epsilon greedy, we'll go randomly. We'll randomly just go either left or right. Or if the number is greater than the epsilon, then we're going to choose the maximum action. Okay, maximum. So we're only going to use the maximum at that time, because we're exploiting the situation more. So just in a few minutes, we will see when I write the choose action function, the helper function, choose action, I'm going to have that if condition. It will show you. Okay, so I'm not sure how clear when I'll open the code, how clear it will be for you guys, but let's see. Let me try. So we're going to save some of these values, and then we're going to start writing and typing the code. So this laptop is not that great. I've never installed Python or Anaconda. By the way, I've installed Anaconda, and I've been working with Anaconda for quite a while now, and I've been very happy about it, because it takes a lot of configuration issues from me. It's just like, in Linux operating system, you may have to use quite a lot of commands. So it takes that burden away from you. It's kind of a visual, like, user interface that you can use to install multiple different packages or take the complexity away from you. So what I'm going to do is, by the way, I've also typed that code because I knew that we were going to run out. We were going to run out of time. What's going on? Oh, it was slow. All right. So then what we can do is, I think I can do this. Yeah, something like this. Right? So I'm gonna so I think this is for sure that we're going to have at least one more session on reinforcement learning next week, because this is just one example. I think I have at least 6 or 7 different examples ready for reinforcement learning, many different problems. And then I also have the robot, the ant robot that we're going to use to train. And that's when we're going to see how we can learn in a continuous state space and continuous action space, because this is going to be discretized version. Ant robot, we're going to have the continuous values, and we're going to implement a slightly more advanced version of reinforcement learning. But let's go with the very simple one, the simplest that I've chosen so far. Okay, so what we did was, well, I'm going to use NumPy. NumPy, it's a library to basically deal with the data structures and several other operations on data structures. So I'm just going to use some built-in functions for that. So I'm going to import. By the way, can you guys see it? No? Better? Okay. And then I'm going to use the environment that is going to visualize the cart, and the pole moving, and visually show the game structure. Okay. So I'm going to import both of these. I'm going to use NumPy and P and Gym. I hope everybody knows about that, how to import a library to use in Python. I'm pretty sure that some of you are pretty new to Python. So I said that there are 4 possible variables, right? 4 states. 4 states. So all what I'm doing in here is I'm going to use a linspace function, built-in function from NumPy that converts a continuous variable, not converts basically. It discretizes a variable between a range, specific range. I'm going to provide a minimum value, a maximum value, and I'm going to say discretize it and generate this many number of values or numbers between this minimum and maximum value. So if I don't do this, then it's a continuous space, continuous state space, and it's going to be incredibly difficult to solve problems using Sarsa. We're going to have to discretize our state space into discrete values, okay, for now. So I hope that you guys understand. So whole theta space, meaning the state space, whole theta space, whole theta velocity space. Remember, we said we had 2 variables or 2 states for the pole, theta and the velocity, right? Velocity of theta. So I'm using theta from minus 0.209 to 0.209, and I'm just generating 10 values. Okay, I'm just discretizing it. I'm saying that in a state, theta state space, we can have 10 different possible theta values. You can have 20, that's fine. I just use 10 to keep the state space small enough so that my computer can solve that within just a few minutes. Okay, and then we have the velocity, right? -4 to 4 theta velocity space. Okay, I didn't use the units. Don't worry about the units at this moment. When you solve the real world problem, your states are going to have to be much more meaningful than what we have here. Okay, but this is just an example. Then we have the cart position. The cart position is the x value of the cart position is from -2.4 to 2.4, and there are 10 values in it. Sounds good? Then I have the cart velocity, how fast the cart is moving, can move. It's from -4 to +4. Again, please don't ask me about the units here. It can be miles per second or meters per second or centimeters per second. It can be anything, okay? Well, then what we do is we have 2 helper functions, get the state and choose an action, right? Get state gives us, we take a certain action, we get into a certain state in the environment, and then that environment that is created is going to give us the value of that state, where you are exactly. Okay, where you are exactly in the environment. So if you look at the lines 11 to 14, how many different possible states our entire complete environment we can have. How many different possible states are there? 10,000. It's 10 by 10 by 10 by 10. It's a 4-dimensional environment or 4-dimensional state space that we have. Once again, usually real world problems are not that simple. Okay, it's just like only 10,000 states that we are having, right? Okay, great. So just to solve the problem, we have done this. Usually it doesn't work like that. All right, so we get the state. Where do we get the state? Well, we take a certain action and we observe the environment. We perceive the environment. And then after observing the environment, we find out what next state we are in. And what is going to be the state? Well, all those 4 possible values, right, Ronald? 4 possible values, right? So we get the state from the observation. We make an observation from the environment, and then we get the cart x value, cart x dot. By dot, I mean it's like a derivative. How fast we have. Cart x dot is basically the velocity. So I'm just simply using the derivative as a dot instead of velocity. You can call it anything. Okay, that's the variable. So we get the 4 different states after observing the environment, right? The cart, what is it? Cart position, cart velocity, pole theta, and pole theta velocity. So I get these 4. So cart x dot, cart theta. Oh, I should have used pole theta here. Okay, my mistake. I called all of them cart. Okay, from the observation, we just get that. Because we get the continuous values from here, I'm just going to use the digitize. So get a continuous value and just simply give us an integer value of the state. Or a digit, basically, not the integer, sorry, the digit. Like representing one of those states. So I'm going to use the np.digitize to get basically the cart as the value that we have, and then we use the cart position space that we have and look at these 2 values, and it's going to give us the integer value. All what it's going to do is it's going to take a continuous value and it's going to convert it into an integer, and it's going to return that and give us a specific value for a specific state. All right, then we will have to return that. Our function will return that value. Now here, this is an interesting function. Choose action. Okay, so we're in a current state. We need to know what state we are in at line number 26, right? We get the state. Basically, we just use the same function that we have gotten. We're in a certain state, and now we have to choose an action. We have to be in a certain state. We have to observe what state we are in before we take a certain action, right? So we find out what state we are in from the get state function. And then I said, generate a random number, right? Random number is basically np.random.random. It generates a random number between 0 and 1. Okay? If it is less than epsilon value, remember this is an epsilon greedy algorithm. If it is less than epsilon value, then just simply take a random action. Look at line number 28. All what it is doing is I for I in range. And what are the ranges? And number of actions. What are the number of actions? What is the number of actions that we have? 2. See, n actions equal 2. I've just defined n actions equal 2. 1 means left, 2 means right. That is it. So line number 28, what it's doing is that it generates I for I in range and actions. It generates an array of 2 numbers, 1 and 2, and then it picks up randomly, either 1 or 2. That is it. That is all what line number 28 is doing. Okay, generates 2 numbers and then picks a random number between 1 and 2. Okay, sounds good? So take a random action, otherwise do what? Otherwise choose the best action. And how do we choose the best action? We use the max value. So initially, everything is going to be 0 in the entire game structure, right? Everything is going to be 0. Everything is going to be completely random, and it will basically just provide you the first possible action. But as you move along, as you have more and more observations, your policy is going to shape your actions are going to give you better rewards because you have learned from the previous states. Okay, so then the max function is going to play its value. So action values for I and number of actions, and we get the Q. We will get to that Q part soon. Because you see, choose action, it is receiving Q values as an input argument. What are the Q values? Remember, what does Q have? QSA, right? Q needs to know the state, what possible state we are in, and what possible action that we can take. So it will be, for n-step salsa, it's going to be a 10 rows, like I can be in this specific state, and from that state, I can take either left or right. Right? It's going to be a 2D array. Make sense? Okay. So take the best action and then simply return the action. Line number 35, we'll start with the main function. Line number 35, we're going to get the environment. We're going to create the environment. And that's where Gym plays the role. The Gym, OpenAI Gym, environment that we have. See gym.make cardpool version 0. I'm just using version 0. Just there's no specific reason for that because I did it quite a while ago. So I just used the first version of the environment. Well, then we have the alpha. Remember the equation? Q of SA equals Q of SA plus alpha, then brackets, reward plus gamma, and then Q value, right? Reward plus gamma. So we need to have alpha. If I go to this, where is my? So you see here, we're going to use this function. We need alpha, we need gamma. So alpha is the learning rate, how fast we learn, or how slow do we learn in the game, right? And then we need the next state, current state, etc. Okay, so we're going to have to implement this equation in the algorithm. If you look at this algorithm, okay, so where is alpha? Right here, if you look at this step. Okay, so right now we're gonna start basically with initializing the Q values, initializing the policy, and initializing alpha and epsilon, right? Alpha and epsilon. So we're gonna initialize the alpha, we're gonna initialize the gamma, and we're gonna initialize the epsilon. Epsilon is 1 because initially we just want to be completely random, right? So then initially we have to initialize our state space, right? So I'm using 4 nested loops. It's not a, by the way, I don't recommend you to program this way, by the way. Don't do that, okay? Because if I start following either the functional programming standards or object-oriented, it's going to take a very long time. We're not going to be able to finish within half an hour because then I'm going to have to start building the classes, then constructors, and objects, and structures, etc., and then having the correct calls. We're not studying software engineering right now here, but please don't tell your instructor from the software engineering that we program this way. So let's keep it between us here, okay? It's not a very, I'm just using the 4. Still, look, I'm just using the 4 nested loops. I can have a much better way to initialize the state in Python, much better way than this. But it was just that I was coding it really fast, and I was like, let's go and let's see how the actual algorithm that we're going to talk about. The focus is on that, not about how, like, we're not trying to be engineers here, software engineers here. Okay, software engineering has a lot more to do with basically how to program. What are the best ways to program, right? It's not just only about developing a working version of software. A working version of software that basically follows all the standards that we have. It has to be efficient, it has to be secure, it has to be maintainable, reusable, etc., etc. So we're not following that for now. Okay. So what these 4 lines are doing is that in the state space, all what I'm doing is I'm just initializing the state space with 0, 0, 0, 0, 0, 0, everything. Okay. Well, not 0, 0, sorry. I'm using basically the values from the state space that we have just created, right? and I'm just filling that up. Then the first line of the algorithm says initialize QSA arbitrarily, because we don't know any action, possible action, because we haven't played the game at all, right? So what we need to do is we need to initialize so that we remember what the Q values would be. Oh. So all what we are doing is it's slow. The TeamViewer connection is slow. Okay. So for all possible actions, I don't know what's happening. Okay, I'm gonna close a few things on my end to just hope that it gets better. Okay, so these are just the Q values. Initially, everything is 0, 0, 0, 0, right? Make sense? Then we're gonna look at 16 steps ahead in the future. So remember, I expanded that and I said if n goes to infinity is Monte Carlo. So I'm going to look at 16 steps ahead in the future for the card 4, okay, game. And then I'm gonna see like what is the best action or update the values, right? So I need to have the states memory, I need to have the action memory, and I need to have the reward memory. As I just mentioned, n step SARSA, SARSA, state memory, action memory, and reward memory. For how many steps? For n steps. For here, we're just doing this for 16 different steps. So n equals 16. And I'm going to learn the game for 100,000 times. I'm going to run 100,000 episodes. By the way, we are right here in the slide. We're right here. You see all store action operations like state, action, and rewards. We have initialized those, and now we have created 100,000 episodes, and then we're gonna repeat. We're gonna initialize the store, the state, and we're gonna run till infinity. I'll tell you why we will run till infinity in here for this game in just a few minutes. Okay, so we have n episodes. For those episodes, well, definitely we're not done yet because we haven't started learning. This score, what is this score? This score is that G value. Remember, immediate rewards. So we have to calculate or get the cumulative rewards. Oh, we have 5 minutes left. G. Immediate rewards. We have to calculate them and we have to sum them up to use that in our equation. So I'm going to call it a score instead of a reward. I'll call it a score, and then I'm going to use that. And then for the time t, this is the time step. How many steps I'm looking ahead in the future? So I have to go all the way up to 16 steps. So this is another variable that I need to see for how many steps do I need to check in the future. So that's just to manipulate the n value that we have. So I'll tell you just in a few minutes. No way. You're kidding me. It's really hot. I don't know. I really don't like this laptop. Let's see. I really wish that it allowed me to. Okay, it's letting me connect again, which is good. Okay. All right. So what I do is I get the score and then observation. So every single time when the episode is finished, I have to reset the environment, right? I have to reset, go back to the initial version of the environment. So I have to reset. This is the built-in function. I have to take the action. Remember that we are at the dark circle, right? That means we are at the action. We're taking a certain action. We're getting into a certain state, and then we're looking further, like we're unfolding the steps in the future. So what on earth is going on? Right? We take a certain action, we put that action into our memory. Which action did we take? Because we now need to record memory experience replay, right? We need to record each action that we took for the next future, like 16 different steps. And you know why we did T mod n? Because T can go way beyond 16, the value 16, because we're playing the game for an infinite amount of time until the game ends. So T goes from 0 to all the way, until the end of the game. But all what we have to remember is the next 16 steps. So as soon as T goes above 16, it goes mod n, and then it starts from 0 again. Right? Like T index from 0 to 15, as soon as T's value is 16, T mod n, 16 mod n, it goes to 0 again. So we're just updating the index in a smarter way. All right. We get the observation, we store that into the memory, and while not done, this is actually this part. So for T, where is it? For T, all the way until the game ends. Okay. So we start basically here, take an action, observe, blah, 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 blah. If it is terminal, then update the index, T equals T plus 1, right? Because we're just going to get into the next step. Else, select and store an action. Okay, let's check. Let's check that. So we get the observation, right? We take an action. So we took a specific action. We took a step in the environment, and the environment provided us the observation, the next step or next state. We get the reward. We see if the game is finished and some information. These are the built-in return values that the environment provides us. We don't need to be worried about this. So we need to get the cumulative reward, right? Then we get basically the next state observation, the next reward memory, we put that in our reward. If game is done, then T change it from infinity to T plus 1. So episode is ended here because the game is ended. Otherwise, we'll keep running it. Action, choose action. We take an action again. Now you see here, we're doing that for 16 different steps, for 16 next steps. So we will continue doing that. We choose an action, we get the action memory, we put it into our action memory. And now this, how we just initialize this new variable, T minus n plus 1, meaning we will calculate the reward, immediate reward for 16 next steps, T minus n plus 1. So T minus n plus 1 is going to give us the ability to calculate this G value for the next 16 steps. You see, T minus n plus 1, n is 16, right? So T will start from 0 in one episode. So T minus n plus 1, right? Minus 1, right? So then, no, minus 15, minus 15, minus 14, minus 13, all the way to 0. So those are going to be the 16 steps for which we're going to add the reward, cumulative rewards, right? So that's what we're going to do. If tau is greater than or equal to 0, if it becomes greater than or equal to 0, what we're saying is that now in our planning, we went 16 steps far in the game. We're going to go all the way back from step 0 to all the way to the current step, and we're just going to add the reward for the last 16 steps. So how do we get the last 16 steps? Well, from minus 15 to all the way 0, right? So that's all what we get in here. And we calculate this, G value, gamma power J minus tau minus 1. If you remember, we have been writing that equation quite a lot. Remember, G equals RT plus 1 plus gamma RT plus 2 plus gamma squared RT plus 3, et cetera, et cetera. So is that equation. All what we're doing is we're simply implementing that equation. Remember, gamma and then the reward for how many times? For 16 times, simply. Then we add the sum. Then we basically get the, so I'm gonna run that. Hold on, I think there is a version that is much faster than this that I'm gonna be able to run and see for how long we will be able to run. Okay, monitor. Okay, I'll have to close it and open again. No, I have to select the. Okay. Okay, we're running. Actually, we have run up. Let me see if I'm running such program. Ah, okay. Watch this. Has it frozen? I think it has. Yep. But I wanted to show you that the game, but actually, let me try to close it. I promise that we will go over this example in a much more detail on Monday next week. But I wanted to show you this. So you can learn the policy, okay? A policy, because we initially said that we are going to interact with the environment and then learn the best policy, right? We're going to learn the best policy. What you can do, what you can have is, you can still have your agent learn the policy, but it may not be the most preferable policy. So this is basically from Berkeley. They developed this helicopter, and the idea was to basically use reinforcement learning to have it fly, as long as possible. But there can be multiple policies to learn how to fly, right? So they learned a policy. Now it can fly, which is great. But it has learned a policy that is not correct. Okay, it can still fly, but it's flying upside down. Okay, it's still correct. It's letting the helicopter fly, but it's not basically, very pleasant to see. You see how basically reinforcement learning starts. How to train a robot to walk. Initially, in the initial episodes, it does something like this. The episode ends. As soon as it falls down, it just ends. So it does several steps like this. And then after that, after several iterations, it actually learns how to walk and then starts learning how to, how to run, and then becomes an expert. We're gonna have this ant. So if any of you or if any of you or a group of you guys are interested, then let me know. We're going to talk about that. This is very funny, by the way. This is how they learn first and learn how to play. It looks like they're dancing. Remember, we said that designing a robot, reinforcement learning agent robot, is not only just going to be the hardware. If you're designing a robot that has to play soccer, your video has to be very stable too, right? So these are all the reinforcement learning agents that are basically that have been trained. And this guy, it actually looks at an input and then it matches the input and increases the score automatically. It's the computer vision. So reinforcement learning via computer vision that has been implemented. It actually looks at the image and then puts the cube in that situation where it has learned. Okay, so sorry. Yeah, yeah. I mean, it's all. I think there was one more that I did, but let's have a complete session on Monday to go over a couple more, real world scenarios that we're going to solve using the code. Actually, we'll start with this example of the code because we haven't been able to finish it. Okay, I'll post this code online so that you can play with it, install the environment, and then see how the programs work. Okay, and then I promise I'm gonna go over the code examples of how to train a humanoid robot, how to train a cheetah, and then we're gonna do the ant robot example next week.